As you may guess from the title, I'm going to talk about pre-processing in the effect of pre-processing on the physical properties of early type dwarf galaxies. This is not a work introducing a survey or using a large number of data, but this is actually an interesting science case for all those people who are working on the large surveys, particularly inside clusters and galaxy groups. I have not done this project alone, so you can see the list of my collaborators here. And the talk today is organized as follows. So I will speak first about what is pre-processing and why we should care about pre-processing. And then I will introduce you a sample, a small sample compared to the surveys we are hearing today about, a small sample of early type dwarf galaxies that are great candidates as to be pre-processed, great pre-processed candidates. And I will explain that how we can find these type of galaxies given their stellar population properties in groups and clusters. But first of all, in order to make sure we are all on the same page, a very brief introduction on early type dwarf galaxies. So these are low mass galaxies, less than 10 to the 9, 10 to the 9.5, making them a great testbed to investigate the effect of environment on the evolution of galaxies. They are one of the most abundant type of galaxies in the universe. Particularly, you can find them in groups and clusters, so high density regions, but also you can find them in low density parts such as voids and filaments. They are, as you can see from the picture over there, NGC 205, one of the most famous cases in our local group. They are dominated by red light, meaning that they have all the stellar populations, and also studies show that the star formation rate in this type of galaxies is very low, if any. And despite the fact that they are one of the most abundant type of galaxies in the universe, we are far from a detailed picture that how these type of galaxies have been formed. Many scenarios have been proposed thus far. Two of them have gained further attention. One of them is actually based on the lambda CDM paradigm, introduces early type dwarf galaxies or galaxies similar to early type dwarfs as building blocks of the universe. So these are the galaxies that have been formed earlier in the universe, and then they merge together to construct more giant structures, more giant galaxies that we see. And according to the scenario, we think that at least a subpopulation of present-day early type dwarfs that we see today in clusters and groups, particularly in the central parts, are those building blocks that formed earlier in the universe and evolved passively. And the second scenario introduces early type dwarfs as remnants of late type galaxies that have been transformed because of the environmental effects. And by environmental effects, we mean like ram pressure stripping, tidal interactions, anything that can happen to a galaxy inside a high density environment. The second scenario have gained further support by a lot of observational and theoretical work. I have summarized only a very few of them here. As an example, I'm showing you the work done by Smith et al. Here in 2009. So here you are looking at about 100 early type dwarf galaxies in the Coma cluster. On the y-axis, you can see age, metallicity, and alpha over Fe. And these are plotted as a function of cluster-centric distance. So according to their results, the stellar populations in the early type dwarf galaxies that are in the central parts of the clusters, they are older, metal poorer, and more alpha enhanced. And as you go to the outskirts of the clusters, the population grows younger, metal richer, and less alpha enhanced. This is nice. This can be explained by the environmental effects that we talk about, by many theoretical and simulations. But this type of studies have two main problems. The first one, as you can see, is that, both of them contributes to the scatter that you are seeing over here. So the scatter in the central part, we know is coming from the projection effect. So meaning that a galaxy that you see in the center of the cluster can be in the center or anywhere between you and the center along the line of sight. But in the outskirts, the effect that contributes to the scatter is the pre-processing. So we were hearing about that. And this is the effect that is usually coming to attention for galaxies that are in the outskirts of the clusters. What is pre-processing? Galaxies come to the clusters not just individually. They come also as gravitationally bound members of galaxy groups, or also they can come from filaments. So they are already in high density environments long before they come to their present-day host halo, present-day cluster or group. meaning that they have been exposed to these environmental effects that can affect their that they can affect their properties partially or completely. This is what we call pre-processing. And pre-processing is very important because according to the studies and simulations, up to 50% of present-day population of clusters are made up of pre-processed galaxies. So if you neglect the pre-processing, you are putting too much credit to the present-day clusters or groups in transforming galaxies' properties. And in this case, you cannot really interpret the galaxies that are completely quenched or they have these early type morphologies and you can't find them in the outskirts of the clusters and groups. That's why pre-processing is important, and I think this is the time that we start to focus more on the pre-processing and its effect on the properties of galaxies. But the question for observers such as me is that how can we find pre-processed galaxies, or what are the effects of pre-processing on the physical properties that we can actually measure in present day cluster or group galaxies? And this was the question I was trying to answer during my PhD, and for that I needed a sample of pre-processed galaxies, right? And they should be dwarfs because they are they are one of the abundant type of galaxies in the universe, and they are very susceptible to the environmental effect. The search for such type of galaxies started in 2018 by Thorsten Lisker. They went to the Virgo cluster. This is a very near galaxy cluster to us, and also it is dynamically still evolving. So this is not a relaxed cluster, meaning that there are a lot of substructures in this cluster, and it is still in the process of shaping and forming. So it's a great test bed to find pre-processed galaxies and accreted substructures. So they went to the Virgo cluster and they decided to investigate the distribution of Virgo galaxies on the phasal space diagram. Phasal space diagram is a very handy tool for observers for many, many reasons that I don't have time to discuss them right now, but we can definitely discuss them during the coffee breaks. So here you can see all the galaxies in the Virgo cluster. They are beamed according to their absolute R-band magnitude, because if you put them all together, there are a lot of information that will be missed in the very crowded plot. Here, galaxies of different physical morphologies are color-coded differently. We are interested in orange data points. These are early type galaxies inside the Virgo cluster. And they started to do several statistical tests to see if they can find pre-processed accreted galaxies, recently accreted galaxies, according to their heliocentric velocity and their distance to the M87, central part of the Virgo. And according to their statistical studies, which are completely explained, perfectly explained in Lisker et al. 2018, and I will not go through that, they figured out that in this particular part of the phasal space diagram, for galaxies between -17 to -18, there is this suspicious gathering of 9 early type dwarf galaxies in this particular part of the diagram. It means that all these 9 galaxies have similar velocity and similar distance to the center of Virgo. This was suspicious, and this could be a candidate of pre-processed galaxies, galaxies that came all together. But to confirm that, they went to the simulations, to the embodied simulations, and they modeled a case that you have a galaxy group of 10 to the 13 falling to a galaxy cluster of the same size as Virgo, 10 to the 14, along the observer's line of sight. And they started to track the distribution of the galaxies that belong to these two halos through the time on the phasal space diagram. And they figured out that 2 to 3 gigayears after the accretion event, galaxies that once belonged to the galaxy group mimic a similar distribution on the phasal space diagram over here as these 9 galaxies over here. And that's why they concluded that maybe these 9 early types that we have in Virgo are pre-processed galaxies that once belonged to a galaxy group, and 2 to 3 gigayears before, earlier than today, they fell into the Virgo cluster. Again, we are looking at the Virgo cluster. We are looking at one snapshot of the evolution of Virgo, and we want to find pre-processed galaxies. So this is not easy for observers. We cannot track them. We can simulate, we can look at the phasal space diagram and try to figure out like what has happened to these galaxies. Using a different method, again based on the phase space diagram, we also confirmed the accretion time of 2 to 3 gigayears to the Virgo for these 9 dwarf galaxies. That is explained in Bidaran et al. 2020, and I don't have time to explain it now, but we can discuss about it later. And that again emphasizes on the importance of the phase space diagram for people who are working on the clusters and groups, especially people who are observers. Okay, let's jump to the results because that's important. So we observed these 9 galaxies using MUSE. These 9 galaxies, as you can see on the top, all of them have early type morphologies very similar to other early type dwarf galaxies that you see inside the Virgo cluster or Coma cluster or Fornax. They have very similar stellar masses, 8.9 to 9.2, and using MUSE, we decided to investigate their stellar population properties because that's the fossil record of what has happened to the galaxies. Two sets of analyses have been performed on these galaxies, one based on the leak indices, which is a pretty common way of analyzing stellar populations when you have high signal to noise data. And in this case, we had MUSE, which provided us more than 100 signal to noise of more than 100, even in the outer skirts of these low mass and low surface brightness galaxies. We decided to use MGBH beta. The beta is not shown here, sorry. And 2 iron lines. We did the fitting through a 4-step fitting routing based on Chi2 minimization approach. And in this case, we measured age, metallicity, and alpha over Fe. This has been performed on one single spectra per galaxy. We decided to mimic a similar situation that we have one long slit spectroscopy or one spectra per galaxy, and also to have the chance to compare our results with a larger number of results available in the literature. And also the second set of analyses was using Starlight, which is a full spectrum fitting routine, because we wanted to first of all compare the results, the age and metallicity that we get between these two methods, and also for deriving the star formation history. All these analyses were based on the Miles stellar library, and the characteristics of the single stellar population models that we used are described over here. So to compare the results that we get, we compare our pre-processed sample, shown in dark red, with early type dwarf galaxies in the Virgo and Coma cluster, Virgo in pink, Coma in gray, which, sorry, you cannot see it here, but it's visible here, sorry. Okay, I will explain it. But before going to anything, jumping to any conclusion, I have to emphasize all the galaxies compared here have similar stellar mass. So any differences you see here is not based on the stellar mass. It's based on the environment or anything else, but not the stellar mass. The stellar mass has been kept fixed. In terms of age, we didn't see any difference between our pre-processed sample and the galaxies in the Virgo or Coma cluster. But what should bother you a little bit is that why 9 galaxies come to Virgo at the same time 2 to 3 gigayears ago, and they have this wide range of a stellar age. This could be maybe the very first imprints of pre-processing. In terms of metallicity, we didn't see any difference between the Virgo galaxies, so the pre-processed one, and other galaxies inside the Virgo cluster, but we could see a systematic shift between the Virgo DEs and the Coma cluster. This could be because of many different reasons. I don't know. If you have any idea, come and please talk with me. Could be because of the dynamical state of Coma and Virgo, or because of a lower number of galaxies investigated inside the Virgo cluster. But in terms of alpha over Fe, we saw a significant difference. All the 9 pre-processed galaxies have high alpha over Fe compared to galaxies in the Virgo and Coma. Again, I would like to emphasize these all have similar stellar mass. So the difference is not because of the stellar mass of these galaxies. And this could be footprint of pre-processing. That's why we decided to dig a bit deeper. Before that, I have to mention that why that high alpha over Fe is interesting. Because first of all, such high alpha over Fe is expected in the central part of the clusters, but these 9Ds are in the outskirts of Virgo. And second, because such high alpha over Fe is not expected for dwarf galaxies. And if you see them in dwarfs, dwarf galaxies have lower alpha over Fe compared to more massive ETGs. And if you see such high alpha over Fe, not even that high, but you can expect that for galaxies that have been inside the clusters or inside the groups for much longer time, more than 2.5 gigahertz. This is the work done by Galadzi et al. Using SDSS galaxies, and as you can see, ancient infallers with more than 2.5 gigahertz exposure to their present-day environment, they have higher alpha over Fe. But the 9Ds I'm investigating and talking about here have shorter exposure to the Virgo cluster. So quickly, just very quickly review the final results. We decided to first look at the maps because it's Muse. So we have the age, metallicity, and alpha over Fe. We can derive it for the maps of these galaxies. The maps are published in Bidaran et al. 2023. So if you are interested, you can go and check that. And also we decided to have a look at the star formation history because alpha over Fe is a tracer of the star formation history. So here on the top, we have the star formation history for the central part of the galaxies within zero point 0.4 effective radius. And in the bottom, you can see for the outer skirts of the galaxy. And we found that for 6 galaxies in our sample, we have this peak of a star formation at the time. These are the two estimates of the infall time of these galaxies to the Virgo. At the time of their accretion to Virgo or after that, this could be because of ram pressure exerted on these galaxies, compressing their gas in the central part and initiating another phase of a star formation or enhancing a pre-existing one. But because the duration is very short, this can contribute to the high alpha over Fe that we saw. And for the other three, we saw that they have formed most of their mass long before they come to the Virgo cluster. By definition, this is pre-processing. And because the duration for which they took them to form their stellar mass was short, this could contribute to the high alpha over Fe that we saw, and I just explained about it. The last but not least, the high alpha over Fe also and the pre-processed nature of these galaxies also contribute to their chemical enrichment. So this is the very famous Mg over Fe versus Fe over H plot that we see usually for Milky Way. Here in the back, we have the average profile for the Milky Way just for the eyes so they can compare, because I know for Milky Way we are looking at individual stars, but I'm talking about IFU and integrated light, so this is not an apple-to-apple comparison. But what is interesting here is that our pre-processed galaxies, these colorful profiles, which are the average of the beams that we have and the measurements that we have for each beam, they have shorter profiles compared to equally massive Virgo early type dwarf galaxies that are in the Virgo and they are not pre-processed or they are not accreted very recently. There is a truncated profile over here. Here we are looking at the central part of the galaxy and here is the outer skirt. So the truncation is in the central part. It cannot be because of the signal to noise. And we believe this is also because the high alpha over Fe and low metallicity that I just explained to you. And this can be another footprint of pre-processing. Okay, I tried to compress 3 years of PhD in 15 minutes, which is obviously impossible. So I skipped a lot of details and a lot of interesting discussions about these galaxies, as you may have guessed, but they are all presented in these two papers over here. So if you are interested, please go ahead and check them or come and talk with me. I'm always happy to talk about dwarf galaxies. I tried to show how we can find pre-processed galaxies, early type dwarf galaxies, inside the clusters and inside the groups. But this study is just maybe an interesting science case for those of you who are working with large scale surveys. And please, if you have that and if you are interested, do that, because literature is currently suffering from this type of studies, pre-processing effects in the stellar population properties, or in general, properties of dwarf galaxies, particularly dwarf galaxies. And that's it. So thank you so much.